Hello, and welcome to our video on using the inverse Fourier transform. So in the previous video, we defined what the inverse Fourier transform is via the principal value integral, and talked about some cases in which sufficient hypotheses on a function f and its Fourier transform f hat give you the inversion theorem for the Fourier transform. Now we'll use the inverse Fourier transform, perhaps surprisingly, to calculate regular Fourier transforms. Namely, the inverse Fourier transform, with a little bit of trickery and a little bit of elbow grease, will help us figure out Fourier transforms whose integrals would be hard or perhaps impossible to do by hand. Remember that evaluating the Fourier transform requires you to take an improper integral over the whole real line, and if you don't have a really simple function or a really obvious antiderivative, you can go to some pretty unhappy places pretty quickly. Here's an example. Take f of x to be the sinc function. So sinc of x is sine of x over x. We want to find f hat. Now you probably met the sinc function, even if you didn't call it that, back in calculus when you were studying limits and L'Hopital's rule. And we know that sinc is continuous on R, in fact it's C infinity, if you define sinc of 0 to be equal to 1. On the other hand, the improper integral from minus infinity to infinity of the modulus, or in this case absolute value, of sinc of x diverges. So sinc is not an L1. The divergence of this improper integral is tricky, and I outline this in the appendix, which you're welcome to read or omit, and it involves doing a careful and somewhat unpleasant lower bound on the integral that shows the integral of this absolute value of sinc is bounded below by the harmonic series, by summing like reciprocals of integrals. It's pretty weird, but also kind of fun. So the point is, sinc is not in L1 of R. So you might say, well, how does sinc have a Fourier transform? Fourier transforms are defined when the function's in L1. Yes, but I claim the following. The improper integrals sinc of x times e to the minus ikx do converge for all k in the reals, so f hat or sinc hat is defined. Remember, the Fourier transform is defined whenever the Fourier improper integral is defined. And if the function is in L1, then that Fourier integral is always defined. But there are L1 functions, such as sinc, for which the Fourier integral is defined even though the function is not in L1. This is one of those times. And since f hat is defined, we also know that f check of f is defined. So f check at k, remember, is f hat at minus k. But this doesn't help us at all. It tells us that these integrals exist, but how do you calculate an integral like the integral from minus infinity to infinity of sine of x over x times e to the minus ikx? You can integrate by parts to your heart's content, and you will just keep getting conversion integrals, but integrals that don't come out to any good value. So what do? We need to go back to a problem that we solved last week. I'm going to define g of x to be 1 if x is between minus 1 and 1, and 0 if x is less than minus 1 or if x is greater than positive 1. This tells us the following. G hat of k is root 2 over pi sine of k over k, which in our notation here is root 2 over pi f of k. This is something we figured out was probably our first Fourier transform integral or second Fourier transform last week. So I have this nice function g, and I know that g hat is a scalar multiple of our original function f. And moreover, by integration by parts, as I claimed on the previous slide, the Fourier transform of g hat and the Fourier transform of g check are all defined, which is a little more than we usually get for any arbitrary function. And if I want to calculate f hat of k, remember that's my goal with f being sinc, f hat of k is just root pi over 2 times the Fourier transform on g hat of k. So I flipped around this root 2 over pi and got the root pi over 2, and then I took the Fourier transform on f, and so that means I'm doing a double Fourier transform on g. Well, that's not so great, because what's the Fourier transform of g hat? I don't know. But I could also write f hat of k is f check of minus k by my inverse Fourier transform identity. And that's going to be root pi over 2 inverse Fourier transform on g hat evaluated at minus k. So remember, g hat is a scalar multiple of f, so the inverse Fourier transform of f should be a scalar multiple of the inverse Fourier transform of g. And moreover, if I know the inverse Fourier transform of f at minus k, that means I know my original desired quantity, the Fourier transform of f at k. And I like this expression rather more because on the right here I have inverse Fourier transform applied to the Fourier transform of g. And if I'm lucky, a lot of things will cancel out. So let's think about what g is. G is a piecewise C1 function. It's 0 outside the interval minus 1 to 1, and it's 1 on the interval minus 1 to 1. So g is certainly an L1, and it's also piecewise continuously differentiable. So I know what the inverse Fourier transform theorem says. The inverse Fourier transform applied to g hat at big K is g of big K minus plus g of big K plus over 2. So now I'm using the letter big K instead of minus K for the independent variable, and I have my average of the left and right hand limits of g. And those left and right hand limits are actually pretty easy to compute because I have an exact formula for g and it's not too complicated. You'll also note that in this inverse theorem, I didn't have any principal value integrals. And why is that? Because what is the inverse Fourier transform of g hat? Well, that's the inverse Fourier transform of f. And although I don't know how to calculate that inverse Fourier transform of f, but I know that improper integral converges if you believe my integration by parts claim about f. So I have my formula from the inverse Fourier transform theorem. I still have the average of left and right hand limits for g because g isn't purely continuous, but I don't have to worry about any principal value nonsense here. So let's just grind it out. If I have g of k equals 1 for k between minus 1 and 1, and 0 for k less than minus 1 or k greater than 1, what does that tell me? The average of the left and right hand limits of g at a point k over 2, well, if k is less than minus 1, then those left and right hand limits are both 0. And if k equals minus 1, then the left limit is 0 and the right limit is 1, so that's 1/2. And if k is strictly between minus 1 and 1, then the left and right limits are both 1. 1 plus 1 over 2 is 1. And if k equals 1, then the left limit is 1 and the right limit is 0. You get a 1/2. And if k is greater than 1, then the left and right hand limits are both 0, and I get a 0. So hit pause if you need to do the arithmetic, or maybe draw a graph of g and look at the left and right hand limits and grind that out. And one thing we note that's nice, this function g, or rather, not just g, but the average of the left and right hand limits of g over 2, this turns out to be an even function, which will make some calculations later easier. And what do I get at the very end? I know that f hat of k is root pi over 2 inverse Fourier transform g at minus k. And I know that's g at minus k minus plus g at minus k plus over 2. I realize the pronunciation is strange. I'm looking at the limit from the left at minus k and the limit from the right at minus k. And if I just go through what my big piecewise formula for the average of the left and right hand limits is, I see that's always going to be 0 for absolute value of k greater than 1. I see that's 1/2 times root pi over 2 for k equals plus or minus 1. And I see that this is root pi over 2 for k strictly between minus 1 and 1. So I claim that this is what the Fourier transform of sinc is at k. It's a nice, simple, constant piecewise thing, just three different kinds of constants here. And I got all this by thinking about a Fourier transform that I knew from the past and seeing how that related to the function at hand, and then using various hypotheses and integrability and continuous conditions and using the inverse Fourier transform theorem. So it's a good idea to have on hand a stock of basic Fourier transforms, and these are the ones we were doing in the notes and in the exercises, so that you can call on them whenever the need arises to calculate other transforms, regular and inverse, without having to actually evaluate the integral.